Now, we just did previous session an example. We gave an example of how a function can be described using the calculating method, where the function takes the input, especially if it's a number, and calculates from that number what the output should be. Now, the other major alternative way to describe a function is that it uses a table. So it looks at the input value coming in, consults a table to find the corresponding output. So a kind of lookup table idea. So let's now do an example here. So example 0.9 in the text. So you've got a function here, g, f, g, h, whatever. Okay, so in this case g, and the domain is now the cross product or Cartesian tensor. Sorry, Cartesian product of z4 times z4. Now remember, we just did that. What is z4? It's the set of 5 integers: 0, 1, 2, 3. Sorry, 4 inches. 4 inches. 0, 1, 2, 3. Okay, and we take the cross product of that set with itself. So we will have 16, 4 squared, 4 by 4, 16 possible ordered pairs coming in as input values. So 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, and so on. Okay, 16 of them. And the output, you're told, so this is like a description of the function. And we're going to calculate what this output is, what the members are of the range. We will use a table, right? We'll use a lookup table. So we'll take, now the members of this set, remember, are ordered pairs, two numbers, 2 integers, each one from this set, Z4, which is the set 0, 1, 2, 3. Okay, so how to do that? Well, we need the table. So what is this table, this lookup table, LUT? Well, here it is here. Okay. Now, the members of this set, your inputs, your possible inputs, will be able to form I comma j, let's say. And I belongs to Z4, and so does j, 2 integers. Well, to look up the output value, you consult this table, and let's say, so these are the row numbers. Like that'd be row 0. You know, these outputs for row 0. This is row 1. These possible outputs for row 1, row 2, and row 3. Okay, and these columns here, that corresponds to the 0th column, and the 1 column, and the 2 column, and the 3 column. Now, how you actually use this table is you do it in the following way. So so say your input pair here is ij. So you look at the ith row and the jth column. Okay. To find, now let's say it's 1, 2. So it would be row 1. So it'd be this row here, one of these 4, and column. So 1, 2. Okay. So j is 2. So row 1 and column 2. So it'll be this one. Okay. And I'll say it again. So imagine the input is 1, 2. That's your ordered pair coming in. So your I then is 1 and your j is 2. So you look at the 1 row, that's this row here, corresponding to the 1 here, and the 2 column, here's 2, and this column. And where they intersect, if you like, so this row and this column, in other words, this value here, this 3 here, that's your output. Okay? And so, so G of, remember G is your mapper, your function, so it'll map 1, 2, 1, 2 to 3. Now the output of G 1, 2 is 3. This one. Okay. Now, how to remember whether you do the row or the column first? Well, my way of remembering it is R, C. Right? And I just remember as Roman Catholic, RC, Roman Catholic, right? And R stands for row, and C stands for column, RC, Roman Catholic or row column, row first, okay, and then column. So let's do another example. Let's say 3, 2. So the input ordered pair, so the order is important. 3, 2 is different from 2, 3. Okay. So let's do 2, 3. So row is 2 and column is 3. 2, 3. Row is 2. Here's 2, and column is 3. So row 2, column 3. It's this one. So the output would be 1. Okay. So you're looking at a table to choose to find what the output is, and so that's a sort of table-based description of how the function works. Okay? In this case, you have a two input function, with one output. Right? Now another term. So it's an example of a table-based function. All right. Now a new term. A whole bunch of definitions. These few sessions. Arguments. What are arguments? I don't mean kind of argument. I mean parameters. It's sort of like parameters. So when the domain, remember that's the possible input values you can have, the set of possible input values. When your domain of a function is a Cartesian product like this, right? So the input would then be an ordered list of k terms, right? A1, little a1, comma, little a2, comma, dot, little a k. Right? So the elements of this set, and this is a Cartesian product, k with k sets involved in the product. The elements of that set, what I just said, little a1, comma, a2, and so on. Right, here. Oh, tuple, that was the word I was looking, forgotten. Okay, so the elements of this set are a k tuple, right, of this form. Okay, yeah, so you see, that's a good example. Definitions are useful. Labels, terms are useful because you can describe things quickly by using a label. See, I'd forgotten. Couldn't recall quickly this term, a k-tuple. So the members of this Cartesian product set, Cartesian product is a set. The members of this set are k-tuples. Okay, right. Now these. These A's here, the values, they are called the arguments of F. Right? The input values that you have, and you'll have k different kinds. Right? There's a particular value for the first input. This will be a particular value for the second input, and so on. And this will be a particular value for the kth input. So you have k possible arguments, and there may be a range. That's confusing. There may be different possibilities for the values of the first argument, and different possible input values for the second argument, and so on. Okay. Now, so if you have a function that has k arguments, there's k inputs. Like add, the function add we did before has two arguments, right? Two possible inputs, or two inputs. Okay, so A function that has k arguments is, you can call it a k-array. This just sort of makes it an adjective. Right? So a k-array function. Okay? And this k here is called its arity. In other words, just the number of arguments. Right? So the number of inputs, if you like. So it'd be k. Right? Now, if k is 1, you can just call your f, your function here, just a unary function. It just has one input. Right? And if k is 2, well, then it's a binary function. Right? It has two inputs. Now some more definitions. The concept of infix and prefix in the context of binary functions. Now what does infix mean? Well, it's a notation. It's a way of writing something. So in the infix notation, in the context of a binary function, so you have two arguments, right? Two inputs. In the infix, the function symbol, your f, gets written in the middle between the two input values. So was an example here. So say this is the value of your first input, and this is the value of your second input. And this plus sign here, that's your function symbol, plus. Right? So little f would be a plus sign. But look, your f here now is in the middle, right? It's not, you haven't written it this way, for example. See, before we had like f of a comma b, like two inputs, little a, little b. So this function acts on these two inputs to give you an output. Now, if you write it this way, with the function to the left, preceding the arguments, then that way of writing is called prefix. So you fix the position of your function